Early 1943, the Kummersdorf Proving Grounds near Berlin. German engineers circle a newly captured prize from North Africa, an American M4 Sherman tank. On paper, the evaluators are thoroughly unimpressed. It features a dangerously tall silhouette, flat armor plates, and a remarkably average 75mm gun, far inferior to the heavy armor the Reich is developing. But then, a technician climbs inside and flips the ignition. Instantly, the radial engine roars to life. No complex cranking, no agonizing preheating rituals. It just works. In that single, seamless mechanical heartbeat, the unimpressive specifications stop mattering. This immediate start hints at an entirely different engineering philosophy, one that is about to become a strategic nightmare. That classified German evaluation at Kummersdorf did more than just list the technical specifications of a captured enemy vehicle. It exposed a fundamental clash in how two warring nations understood the very nature of modern combat. It forces us to ask a critical question. How did an American machine, one that would be widely criticized by its own crews for severe tactical shortcomings, vulnerable flat armor, and inadequate firepower, become the decisive armored weapon that ultimately broke the Wehrmacht across the Western Front? The answer lies within a fatal German blind spot. Obsessed with achieving absolute individual superiority in every single battlefield engagement, the German High Command engineered complex mechanical marvels, but they completely blinded themselves to the brutal, unforgiving mathematics of global logistics. They were trying to win a war of flawless specifications against an enemy fighting a war of relentless, unyielding availability. The paradox of this conflict is devastating. It proves that a technologically superior weapon means absolutely nothing if it cannot reliably reach the combat zone. To understand why a good enough tank that actually enters the fight will always defeat a perfect machine abandoned on a broken railway car, we must first examine the entirely different industrial realities that birthed them. By the spring of 1943, the global arms race had fundamentally shifted. For the German High Command, the brutal shock of the Eastern Front had rewritten the rulebook of armored warfare. The sudden appearance of heavily sloped Soviet T-34s and impenetrable KV-1s had rendered the early war panzer fleets critically undergunned. In response, the Ministry of Armaments issued a clear, uncompromising mandate: absolute qualitative superiority. German designers were ordered to prioritize vehicle survivability and lethal engagement range above all other metrics. They were no longer building mere cavalry tanks. They were engineering mobile fortresses, designed to destroy the enemy from distances where return fire would be completely ineffective. This philosophy birthed complex marvels of military engineering. The Panzerkampfwagen 6 Tiger, weighing a staggering 56 tons, and the 45-ton Panther were testaments to metallurgical excellence. Their high-velocity guns could punch through almost anything the Allies fielded, while their precisely angled armor offered unprecedented crew protection. But this uncompromising pursuit of battlefield dominance carried a paralyzing cost. These machines were incredibly dense, over-engineered leviathans, demanding massive allocations of rare alloys and highly skilled labor. More importantly, they required an elite, specialized infrastructure just to exist in the field. Germany was fighting a continental land war. Their factories in the Ruhr Valley and Bavaria were directly connected by heavy rail to the eastern and western fronts. Planners could afford to build 50-ton monsters because they operated on the assumption that the national railway system would carry these heavy tanks on specialized flat cars for 90% of their journey. Even their maintenance doctrines reflected this luxury. Replacing a Tiger's overlapping road wheels or extracting a Panther's broken transmission required heavy-lift gantries and specialized recovery vehicles that only a fully equipped rear-echelon maintenance battalion could provide. Across the Atlantic, the United States Army Ordnance Department faced a completely different reality. The American military was fighting an expeditionary war. The industrial might of Detroit and Pennsylvania was churning out unparalleled volumes of steel. But the American factory floor was separated from the battlefield by 3,000 miles of hostile, submarine-infested ocean. This unique geographic constraint dictated every single line on the drafting tables. The United States could not simply roll a tank out of a factory and onto a train bound for the front line. Every single American armored vehicle had to be loaded into the dark, cramped cargo hold of a Liberty ship. It had to be lifted, suspended in midair, by standard commercial dockside cranes in New York or Boston, and then unloaded by equally limited infrastructure at the ports of Liverpool, Casablanca, or Oran. At the time, the lifting capacity of a standard transatlantic cargo crane maxed out at roughly 40 tons. Furthermore, the hatches on these transport ships had strict dimensional limits. Once a tank finally reached a foreign port, the logistical nightmare was far from over. The Americans knew they could not rely on pristine European railway networks, fully expecting that Allied bombing campaigns would reduce French and German rail lines to twisted rubble. Therefore, whatever tank the Americans built had to be capable of driving under its own power, on its own tracks, for hundreds of miles from the beachhead directly into the combat zone. This unforgiving logistical gauntlet forced agonizing, deliberate compromises. The Americans needed a reliable expeditionary vehicle. They could not build a 50-ton heavy tank, even if their designers possessed the blueprints. They had to build a 30-ton medium tank. This rigid weight limit dictated everything. Armor thickness was strictly capped, leaving the crews vulnerable to high-velocity anti-tank fire. The turret ring diameter was restricted to fit shipping constraints, which in turn dictated the size of the main armament, keeping it at a reliable but decidedly average, short-barreled 75mm gun. Even the M4 Sherman's bulky silhouette was a necessary trade-off to accommodate a readily available aircraft engine and a front-mounted transmission. The American engineers knew their tank would not win a one-on-one duel against a heavy German counterpart. They consciously traded lethal range and thick armor for strategic mobility, low shipping weight, and mechanical simplicity. For the German engineers analyzing the captured Sherman at Kummersdorf, these American compromises were glaringly obvious. Viewed through the lens of a defensive land war, the Sherman appeared structurally deficient. When ballistics experts examined the slope of the American armor and the muzzle velocity of the gun, they saw exactly what their doctrine told them to see: an inferior, vulnerable machine that could be easily destroyed by a Panther or a Tiger long before it got into effective firing range. They confidently documented the Sherman's tactical weaknesses, satisfied that German heavy armor would easily dominate the coming battles. But the German evaluators were looking at the wrong metrics, measuring the Sherman as a dueling weapon and completely missing its true purpose. The engineers at Kummersdorf knew the Americans had made severe compromises in firepower and armor. But the true shock, the one that would slowly reveal the fatal flaw in the entire German war machine, came not on the live-fire proving ground. It came when they stepped inside the maintenance bay. The mechanics at Kummersdorf began the routine process of stripping the captured Sherman down to its bare components. They expected to find typical foreign machinery, but instead they encountered an industrial revelation. When German technicians ordered replacement components to be tested against the original American fittings, cannibalizing captured supply crates shipped directly from North Africa, they noticed something deeply unsettling. Every single gear, every sprocket, every bolt fit perfectly. There was no need for a master mechanic to manually file down a housing edge. There was no requirement for custom machining to make a new part align with the chassis. An American component, pulled from a random wooden crate, slid effortlessly into a tank built months earlier in a completely different factory. To the German eye, this was almost alien. The Reich's factories operated on a system of highly skilled craftsmanship. German tanks were built with exacting precision, but they were largely hand-fitted. If a Panther needed a new transmission piece, a field mechanic often had to physically adjust the metal to make it work within that specific hull. The true depth of the American design philosophy materialized when the evaluators timed a major repair. The engineers simulated a catastrophic drivetrain failure. On the Sherman, the entire transmission and differential assembly was housed beneath a bolted steel cover on the lower front hull. The German mechanics unfastened the bolts, attached a standard field winch, and pulled the entire massive unit out in one clean block. Within just a few hours, a completely new transmission could be slotted in, bolted down, and the tank could drive out of the bay. The contrast with their own cutting-edge armor was stark. If a German Panther suffered a broken gearbox, a notoriously common failure, the repair process was a logistical nightmare. The Panther's transmission was buried deep inside the hull, beneath the main turret. To access it, a heavy maintenance platoon had to bring in specialized lifting gantries, physically detach the massive gun turret, hoist it high into the air, and awkwardly extract the broken block from above. A simple mechanical failure paralyzed the Panther for days, tying down heavy equipment and rare specialist crews. The Sherman, however, accepted that parts would inevitably break in combat. It was structurally built to ensure those breaks could be fixed by tired men in muddy fields using basic tools. Here, under the harsh lights of the Kummersdorf garage, the conflict crystallized. It was a clash between German artisanal over-engineering and the brutal, unforgiving efficiency of American mass production. The Sherman was not a bespoke weapon. It was a modular, interchangeable appliance. Yet, a tank that is exceptionally easy to repair in a well-lit bay is still useless if it breaks down every few miles. The engineers knew that quick repairs were a massive tactical advantage, but the true measure of strategic value was survival on the move. A vehicle designed for an expeditionary force had to endure a grueling, continuous cross-country march without the luxury of railway transport. To test this, the German evaluators ordered the reassembled Sherman out of the garage and onto the endurance track, fully expecting its mass-produced components to tear themselves apart under pressure. The Kummersdorf endurance track was a punishing circuit of deep sand, thick mud, and jarring concrete obstacles, explicitly designed to push heavy military machinery past its breaking point. German engineers watched from the observation stands, waiting for the captured American tank to fail. German heavy tanks utilized wide, all-steel tracks. These were incredibly durable against enemy fire and excellent for distributing the massive weight of a 50-ton machine over soft ground. But this design exacted a brutal toll on the drivetrain. Without shock absorption, every violent impact and every vibration transferred directly from the earth into the transmission and the chassis. After just a few hundred kilometers of road marching, the heavy steel track pins warped, the metal ground itself down, and the crew was left exhausted from the relentless, bone-rattling vibration. To the German evaluators, the Sherman's tracks looked inherently flawed, almost fragile. They were fitted with thick rubber pads. To put rubber on a frontline combat vehicle's tracks seemed completely counterintuitive, a glaring vulnerability waiting to be exploited by artillery shrapnel and sharp, rocky terrain. But as the captured Sherman endlessly circled the Kummersdorf track, hour after hour, the genius of this civilian-style innovation became undeniable. The rubber blocks absorbed the shock of the road. They isolated the suspension and the delicate internal transmission components from the violent vibrations of continuous travel. As a result, the Sherman could march at sustained high speeds on paved roads for thousands of kilometers without tearing its own drivetrain apart, without destroying the asphalt beneath it, and without physically breaking the men inside. By the time a German Panther completed a 100-kilometer road march, the crew was often deafened, physically battered, and immediately forced into hours of grueling maintenance just to tighten the sagging steel tracks. The American crew, riding on rubber pads and a simple vertical volute spring suspension, arrived at their destination with their machine intact, ready to fight. When the Sherman finally halted in the testing yard, the evaluators climbed back inside, shifting their focus from how the machine moved to how it was actually operated in combat. Here they found a vehicle engineered with a completely different set of priorities. German heavy tanks were ultimately built around their massive, high-velocity guns. The human crew was expected to adapt to the heavy machinery. The Sherman, they realized with growing unease, was built around the crew. The internal details were startling. At the top of the turret, the commander's station featured a rotating cupola equipped with a 360-degree periscope. A German commander in a Tiger or Panzer IV often had to keep his heavy steel hatch open and his head physically exposed to maintain situational awareness, risking instant death by shrapnel or sniper fire. The American commander could sit safely behind closed armor, spinning his periscope with a flick of his wrist, rapidly scanning the entire battlefield without exposing an inch of flesh. Directly below him, the gunner's station held another technological shock. The American 75mm gun was mounted to a complex Westinghouse gyro stabilizer. This array of gyroscopes and hydraulic cylinders was not designed to make the Sherman a perfect sniper while sprinting at full speed, a common myth of the era. Instead, it kept the main gun roughly elevated on the target horizon, regardless of how violently the tank pitched over uneven ground. When the driver slammed on the brakes, the gunner did not have to waste precious seconds manually cranking the elevation hand wheel to find the enemy again. The gun was already there. In the lethal, unforgiving mathematics of armored combat, the tank that halts, acquires the target, and fires the first aimed shot almost always survives. The gyro stabilizer bought the American gunner a 2-second advantage. 2 seconds was the difference between life and death. But perhaps the most profound revelation was tucked into the side sponson, the radio. By 1943, the Wehrmacht had pioneered the use of radios in tanks, a key component of their early blitzkrieg successes. Yet due to severe manufacturing bottlenecks and reliance on complex components, many German tanks still only carried receivers, with two-way transmitters reserved strictly for platoon and company leaders. The Americans, unburdened by such industrial shortages, installed a standardized, high-fidelity, push-button FM radio in every single Sherman. It was crystal-controlled, meaning crews didn't have to desperately fiddle with dials to find the right frequency while under fire. They just pushed a button, and they were instantly connected. The German engineers recognized the terrifying tactical implications of this. A platoon of 5 Shermans was not 5 individual tanks fighting in the same field. It was a synchronized, communicating organism. Any single American tank that spotted a hidden anti-tank gun could instantaneously warn the rest of the formation, call in localized artillery support, and coordinate a flanking maneuver in real time. Even the internal safety features spoke to a chillingly practical philosophy. The evaluators noted the Sherman's hatches. They were spring-loaded. A heavy steel hatch on a German tank could weigh over 100 pounds. If a Panther took a hit and lost engine power, or if it rolled into a ditch at an awkward angle, heaving that dead weight open to escape a burning fighting compartment required tremendous physical strength from a wounded, panicking man. The Sherman's hatches, under high spring tension, popped open instantly with the simple pull of a lever, giving the crew a fraction of a second more to evacuate. The American designers explicitly acknowledged that their tanks would be hit, that they would burn, and they prioritized getting the highly trained crews out alive so they could simply be assigned to a newly shipped tank the very next day. As these technical reports were drafted, translated, and sent back to the Ministry of Armaments in Berlin, the initial dismissive sneers at Kummersdorf evaporated. Within the offices of WWII 6, the German Tank Design Bureau, the tone of the secret memorandums shifted from technical curiosity to institutional anxiety. General Heinz Guderian, the Inspector General of Armored Troops, had been demanding more reliable engines and simplified maintenance for German panzers, but he was continually overruled by a high command obsessed with thicker armor and bigger guns. Now, staring at the data from the captured Sherman, the more pragmatic German logisticians understood the grave strategic danger forming across the ocean. They realized that the Americans had decoupled the concept of a tank from the concept of a flawless individual weapon. Germany's entire late-war strategy relied on an elastic defense, using highly lethal, heavy armor to counterattack and blunt enemy breakthroughs. But how could the Wehrmacht counterattack an enemy whose supply lines never snapped? The German High Command knew their own grim statistics perfectly well. If a heavy panzer battalion reported 70 Panthers on paper, the brutal reality was that after a 2-day road march to reach the active front line, only 20 or 30 might actually be operational. The rest would be strung out along the roadsides, suffering from shattered final drives, blown engine gaskets, and broken gearboxes, waiting for specialized heavy-lift gantries to arrive. If an American armored division landed in Europe with 200 Shermans, the German evaluators realized with a sinking dread that 200 Shermans would arrive at the front line. The mechanical reliability of the M4 was not merely an operational convenience. It was a devastating strategic weapon. It guaranteed an unrelenting operational tempo. This theoretical anxiety, documented in the quiet testing grounds of Kummersdorf in 1943, transformed into a blood-soaked reality in the summer of 1944. Following the D-Day landings and the agonizing crawl through the dense Normandy bocage, the American military finally triggered Operation Cobra, breaking out of the hedgerows and into the open French interior. Here, the mechanical endurance of the Sherman dictated the entire pace of the war. General George S. Patton's Third Army unleashed its armored divisions in a relentless, sweeping pursuit across France. The American tank columns drove through the night, traversing shattered roads, cutting through open fields, pushing their engines for days on end without stopping for major overhauls. They bypassed German defensive strongpoints before the Wehrmacht could even establish them. This was a war of absolute movement, and the Sherman was a machine built strictly to move. In a desperate response, the Wehrmacht attempted to retreat and reform their defensive lines, pulling their magnificent Tigers and Panthers back to the east, but forced out of their static defensive positions and deprived of their beloved, heavily bombed railway networks. These heavy leviathans were subjected to the very thing they were never engineered to do: continuous, long-distance road marches. The German logistical nightmare awakened with a vengeance. Under the sheer strain of moving 45 and 56-ton machines under their own power, Maybach engines overheated and caught fire. The complex, highly stressed final drives of the Panthers literally shattered from the tremendous torque. Without the specialized 18-ton recovery half-tracks, many of which had been destroyed by roaming squadrons of Allied fighter bombers, or were simply out of fuel, there was no way to tow these broken monsters to safety. Across the roads of northern France, American infantry advancing behind the armored spearheads found a surreal landscape. They passed dozens of terrifying, undefeated German heavy tanks, vehicles that had never been penetrated by an Allied shell, sitting silently by the roadside. Their crews had been forced to do the unthinkable, rig their own engineering masterpieces with demolition charges and abandon them, totally intact but completely immobilized by a broken gear that could not be replaced in the field. The German strategy of qualitative superiority was literally breaking down on the side of the road. But the reality of this operational dominance was far from bloodless. When the two forces inevitably clashed in direct combat, the tactical flaws that the Germans had initially mocked at Kummersdorf proved devastatingly real. In a static ambush hidden among the dense foliage of a French village or a sunken road, a single concealed Panther or Tiger was an apocalyptic force. Its high-velocity gun could easily punch through the flat front armor of a Sherman from over a kilometer away, a distance so vast the American crew wouldn't even hear the muzzle blast before the armor-piercing shell struck. The American 75mm gun, chosen for its versatility and low shipping weight, was entirely incapable of penetrating the thick, sloped frontal armor of a Panther. In these head-on engagements, American armored columns were slaughtered. Shermans burned in the French mud by the hundreds. To a German gunner looking through his Zeiss optics, they were winning the war. They were destroying 3, 4, sometimes 5 American tanks for every one they lost. Yet, despite these localized massacres, the German defenders soon witnessed an impossible, deeply demoralizing phenomenon. A Wehrmacht anti-tank battalion would annihilate an American tank company on a Tuesday, leaving the fields littered with smoking steel. By Thursday, that exact same American company would attack their lines again, seemingly at full strength. The secret lay in the modularity and interchangeability tested in the Kummersdorf garage. The United States Army did not just send tanks to Europe. They sent a massive, highly synchronized industrial ecosystem. Heavily equipped American ordnance maintenance companies operated dangerously close to the front lines. Their standing order was brutally simple. Any tank that can be towed can be fixed. When an American attack was repulsed, armored recovery vehicles dragged the shattered Shermans back to field depots hidden in the woods. Here, the brutal efficiency of mass production took over. If a Sherman had a completely destroyed turret but an intact lower hull and engine, it was parked next to a Sherman that had driven over a mine, destroying its chassis but leaving its turret pristine. Utilizing standard field cranes, mechanics simply lifted the good turret off the mine tank and bolted it onto the intact hull of the other. The standardized wiring harnesses connected instantly. The transmission blocks were swapped in a matter of hours. Hoses were used to wash the grim evidence of the previous crew out of the shattered fighting compartment. A fresh coat of olive drab paint was quickly applied over the patched armor, and within 24 hours, a functionally new tank was driven back to the assembly area. The Wehrmacht was bleeding to death from 1,000 tiny cuts. Every single lost Panther was utterly irreplaceable, permanently erased from the German order of battle. Every damaged Tiger required a flat car and a perilous train ride back to a factory in the Ruhr Valley, running a gauntlet of Allied bombers. Meanwhile, the Americans were not just replacing their losses from the endless shipments crossing the Atlantic, they were rapidly regenerating their own casualties directly on the battlefield. The German strategy of localized, qualitative superiority was drowning in a relentless, terrifying tide of American availability. This was the grand, sweeping triumph of American logistics. The engineering compromises made years earlier on the drafting boards in Detroit had been completely vindicated. By choosing operational endurance and modular repairability over absolute armor and firepower, the United States had fielded the perfect weapon to win a war of continental attrition. To the generals looking at broad strategic maps in London and Washington, the Sherman was performing flawlessly. It was winning the war exactly as it was designed to do. But this narrative of a highly reliable, endlessly repairable machine masked a much darker, far more tragic reality. The grand mathematics of mass production, the seamless interchangeability of transmission blocks, and the operational brilliance of the gyro stabilizer meant absolutely nothing to the 5 young men locked inside the steel hull when an 88mm armor-piercing shell slammed into their glasses plate. The Sherman tank could be quickly repaired, the torn metal welded, and the broken tracks replaced. The men inside could not. The American crews were trapped in a horrific gap between strategic success and tactical vulnerability. They knew exactly how thin their armor was. They knew their gun was largely ineffective against the front of the heavy German beasts. And yet, they were ordered to drive forward anyway. The strategic mobility that allowed the American army to bypass German defenses also forced the frontline tankers to repeatedly drive directly into the crosshairs of the most lethal anti-tank weapons on the planet, knowing that the only way to kill a Panther was to sacrifice 2 or 3 Shermans to get a single shot at its weaker side armor. The tank was an industrial masterpiece, but the human cost of deploying an adequate machine against a perfect one was about to push the American tanker to the absolute brink of psychological collapse. That psychological collapse began in the sunken lanes and dense hedgerows of Normandy in the summer of 1944. Here, in the claustrophobic confines of the French bocage, the initial, dismissive technical reports filed by the Kummersdorf engineers were suddenly and tragically validated. They had been absolutely right about the Sherman's fatal tactical flaws. When forced into tight, close-quarters combat, where strategic mobility meant nothing, the American tank crews faced a terrifying reality. The standard 75mm gun, which had performed admirably in the open deserts of 1942, was now a severe liability. An American gunner could accurately place a round directly onto the frontal glacis of a perfectly camouflaged Panther, only to watch the armor-piercing shell shatter harmlessly against the thick, sloped steel. In return, the high-velocity German anti-tank rounds tore through the Sherman's thin, upright armor with terrifying ease. This created a brutal disconnect between the strategic brilliance of the Allied supply chain and the lethal, intimate reality experienced by the 5 men inside the hull. The Sherman's supreme mechanical reliability offered cold comfort to a crew who understood that their pristine engine and flawless transmission merely guaranteed they would make it to the ambush site. The American logistical machine could replace a shattered tank in a matter of hours, but it was demanding a devastating toll in human lives to gain mere yards of ground. Realizing that a head-on duel was essentially suicide, American armor commanders were forced into a desperate tactical pivot. They could not outgun the Wehrmacht, and they could not out-armor them. They had to rely entirely on what the Sherman was explicitly built for: overwhelming numbers, mechanical speed, and a relentless operational tempo. If a lone German heavy tank commanded a crossroads, the only viable solution was to aggressively flank it, fully accepting the grim mathematics that the lead American tank, and perhaps the second, would be inevitably sacrificed just to give the third a clear shot at the enemy's vulnerable side. This forced reliance on raw speed and continuous momentum over heavy steel would ultimately dictate the entire Allied offensive, setting the stage for the massive armored sweeps that were about to push the Wehrmacht back toward the Rhine. When that momentum finally broke the German lines, the tactical desperation of the hedgerows transformed into a strategic avalanche. By late 1944, and accelerating into the collapse of the Ruhr pocket in the spring of 1945, the American doctrine of continuous operational exploitation violently dismantled the German defensive strategy. The Sherman's core design imperative, the ability to drive for hundreds of miles without requiring a heavy maintenance overhaul, ceased to be just a logistical convenience. It became the primary instrument of the Wehrmacht's destruction. Entire American armored divisions were now swallowing territory at a staggering pace, pushing 50 miles in a single day across the shattered European countryside. The rubber-padded tracks absorbed the grueling punishment of ruined asphalt, while an endless chain of supply trucks kept the fuel tanks full. If a Sherman's transmission failed during the sprint, field mechanics swapped the entire modular block overnight, keeping the spearhead moving at a relentless, suffocating rhythm. The Americans were exploiting frontline breakthroughs far faster than the German high command could even draw new defensive lines on their headquarters maps. In a desperate bid to halt the collapse, German commanders ordered their elite heavy panzer battalions to rapidly reposition and plug the widening gaps. But the very machines that had terrorized the Allies in static ambushes were now caught in a fatal trap of their own engineering. The German National Railway Network, the vital arteries required to transport the 56-ton Tigers and 45-ton Panthers, had been pulverized by Allied bombing. Deprived of specialized flat cars, German crews were ordered to drive their over-engineered Leviathans under their own power. The result was a mechanical slaughter. Under the extreme, unintended stress of continuous road marches, the complex German drivetrains tore themselves apart. Panther final drives routinely shattered under the immense torque of moving heavy steel over uneven ground. High-performance engines overheated and seized. As the Reich's synthetic fuel reserves evaporated, the massive consumption rates of the heavy armor became an outright death sentence. When a Tiger snapped a track or ran dry, there was no quick modular replacement, and the specialized heavy recovery vehicles were nowhere to be found. As the American columns pushed deeper into the German heartland, they encountered a surreal, defining landscape. They were driving past dozens of the most advanced Panthers and Tigers sitting silently by the roadsides or abandoned in village squares. They were perfectly intact. Their famously impenetrable frontal armor was unblemished, but their crews had fled. They had been forced to drop demolition charges down the barrels of their own engineering masterpieces and walk away, immobilized by a sheared gear they could not reach or a fuel tank they could not fill. The roads of the collapsing Third Reich were ultimately littered with these pristine monuments to a fundamental miscalculation. The technological clash had reached its fatal conclusion, proving that the most heavily armed fortress in the world was entirely powerless against an enemy that never stopped moving. It all comes back to that quiet proving ground near Berlin in early 1943. When the German engineers stood around the captured Sherman, measuring the thickness of its flat armor and calculating the muzzle velocity of its short-barreled gun, their mathematics were completely flawless. They had accurately documented every single tactical deficiency of the American machine, but they were measuring the wrong war. They viewed the looming conflict in Europe as a series of isolated jousting matches between knights clad in impenetrable steel. They completely missed the terrifying reality that World War II was not a duel of individual champions. It was an exhausting, mechanized grind of industrial attrition and relentless continental movement. The M4 Sherman was never designed to win a static shootout against a heavy panzer. It was a masterpiece of a vastly different philosophy: the brutal efficiency of mass production, modular repairability, and global supply chains. Its creators deliberately chose to prioritize the mundane, unglamorous realities of modern logistics: the lifespan of a radial engine, the seamless interchangeability of standardized screw threads, and the strict lifting limits of commercial port cranes over the terrifying prestige of thick armor and massive guns. The evaluators at Kummersdorf looked at the Sherman and saw a tank that was easy to destroy, failing to realize they were looking at an armored ecosystem that was mathematically impossible to defeat. The Third Reich poured its dwindling resources into engineering absolute tactical perfection, creating marvels that dominated individual engagements but ultimately paralyzed their own military infrastructure. The United States accepted tactical imperfection on the drafting board to guarantee overwhelming strategic availability on the battlefield. The bitter, undeniable lesson of the armored conflict is that the finest weapon ever forged is utterly meaningless if it cannot be repaired, fueled, and sustained in the mud. Tactical superiority wins the ambush, but strategic sustainability wins the war. In the end, the German High Command engineered brilliant, terrifying machines designed to win a single battle flawlessly. The Americans built a completely reliable machine, explicitly designed to win the entire war.